Well, I was pleased to follow two excellent talks, one on the metal mesh material and one on silver nanowire films. And my talk, like theirs, is focused on overcoming design limitations of ITO on plastic films. A little bit of background, carbon nanotubes is a common thread amongst all of the products in our company. And so just a quick overview for some of you who may not know much about these materials. Carbon nanotubes' molecular structure is essentially tubular graphene. They have nanoscale diameter on the order of 1 nanometer, very high aspect ratio, 1,000 to as much as 10,000 or more. They automatically self-assemble into networks, which is great for forming conductive networks and also reinforcing materials. You have the chemistry of carbon. They're very environmentally stable. They're the world's strongest material per unit weight. And they can be an excellent conductor or semiconductor depending on how the carbon atoms are oriented in the sidewalls of the nanotube. Our company specializes in the synthesis of these materials. We are recognized as being best in class in the single wall and few wall carbon nanotube materials. Some of you may know me and Bob Prino, co-founders of Chasm. We've been in the printed electronics industries for many years, and we founded Chasm Technologies as a consulting business in 2005. In 2015, we made a pivot and we purchased carbon nanotube manufacturing assets and founded Chasm Advanced Materials. Since 2015, we've shifted our emphasis from helping other clients develop and commercialize advanced materials to developing and commercialize our own advanced materials products. Our distinguished capabilities are in the carbon nanotube synthesis, carbon nanotube inks, and as you will see today, we have a unique capability in carbon nanotube hybrids. We have two locations. We have our headquarters and application development center is in Canton, Massachusetts, which is in the Boston area. We have 18 people there. We also have a manufacturing plant and R&D center in Norman, Oklahoma, right down the road from the University of Oklahoma, which is where the carbon nanotube synthesis technology was originally invented. We have 10 people there. We've recently closed a $10 million Series B round that's led by Wave Equity Partners in Boston. We have three business units at Chasm. First is Agent, which is a carbon nanotube hybrid platform that's aimed at providing a unique transparent conductive film solution. We have two other business units. One is carbon nanotube hybrids as well, IDTECHEX, which is nanotube enhanced carbon particles. And one of my colleagues is giving a talk at 12:40 this afternoon on this class of materials, which is also unique. And then we have a carbon nanotube materials business, and we sell carbon nanotubes to the outside world, but most of our production is aimed at supplying carbon nanotubes for our Agent business. Just really briefly, this material, IDTECHEX, nanotube enhanced carbon, is a really cool material. It's not the subject of my talk, but this is an example of a graphite core particle that is carpeted with carbon nanotubes. In this material, graphite is normally used as an anode material for lithium-ion batteries, and this will result in better batteries if the graphite is upgraded to this material. Another version of IDTECHEX is a carbon nanotube mesh encapsulated carbon black. So you have an enhanced carbon black material. Carbon black material is used extensively in tires. This allows tires, we expect will allow tires to get the unattainable triad of long wear life, great traction, and low rolling resistance. We recently announced a strategic alliance with Burla Carbon to accelerate the development and commercialization of those materials. Now back to Agent. It's well recognized that indium tin oxide is the industry leader. It has been for 40 years and continues to be the industry leader. It dominates both glass and flexible substrate segments. It's going to continue to dominate glass. But as has been noted by the prior two speakers, ITO is going to be displaced on flexible substrates, which are mainly plastic films. ITO is not flexible, it's not formable, and it's definitely not stretchable. It's also is not as good on plastic as it is on glass. The transparency and conductivity properties on plastic are inferior to on glass because of the temperature limitations of the plastic. And ITO, as well as the other metal mesh and silver nanowire materials, can be costly to create circuit patterns on the plastic films. What we've done with Agent is we recognize that silver nanowire films and metal mesh films are positioned to penetrate this market that's been dominated by ITO. What we have decided to do is let's make those materials better. Let's combine carbon nanotubes in a clever, unique way to make silver nanowire films better and metal mesh films better. Here you see an example of a carbon nanotube hybrid, which has a silver nanowire film, the shiny rigid rods here, and then this noodle-like structure is the carbon nanotubes that have been printed on top of the silver nanowire film. We have a very simple process for fabricating circuits. It's called print, etch, done. And with print, etch, done, we compare ourselves with ITO. ITO is the cost of the ITO film on plastic, but the cost of fabricating circuits on ITO is much higher than the cost of the film. With ours, we are charging a higher price per unit area versus the ITO, but we have a much simpler, faster, and more affordable means of patterning. And so the end result is the patterned circuit is more affordable than ITO. In addition to being more affordable, we have better performance because of more robust structure here and more flexibility and better optoelectronic properties than ITO on plastic. Let me explain why it's so simple to process circuits using standard printed circuit processing. Here we're starting with a silver nanowire film that is roll-to-roll coated. So this material is available in roll format. And then we print any pattern that can be screen printed. We print carbon nanotube ink on top of that silver nanowire film. And then we etch away the exposed silver nanowires in seconds using ferric nitrate etchant. Print, etch, done. We have 3 versions of product, 75 ohm per square, 30 ohm per square, 10 ohm per square. The ohm per square is mainly dictated by how much silver nanowire areal density is in that film. And there's an expected trade-off in transparency, 98, 95, and 90% for these 3 different ohm per squares. We have 3 different ohm per squares because different applications require different values of sheet resistance. And I'll explain that a little bit more later. The same process flow can be realized with metal mesh film. We start with a metal mesh film. We screen print carbon nanotube ink. The carbon nanotube ink is a multifunctional material. Not only does it make the metal mesh better, it makes it more robust. It makes it perform better, especially in RF applications. But it acts as an etch mask, just like for the silver nanowire film case. The exposed metal mesh is etched away. Print, etch, done. Very affordable, very standard way of making printed circuits, flexible printed circuits. This version, we developed the metal mesh version because applications, specifically transparent antenna applications, do require a lower ohm per square. So that was not practical to achieve that ohm per square with current generations of silver nanowire film. So we developed a metal mesh version of Agent, 1 ohm per square and 90% visible light transmittance. Here is an overall summary of our product portfolio. You can see the different 75, 30, 10, and 1 ohm per square. The transparencies range from 90% up to 98%. The haze values that we achieve are respectable, not versus the optimized silver nanowire films like from C3 Nano, not as low in haze as their products, but we're really not aiming at the same touchscreen applications that they are. But our haze values are respectable, 0.7%, 1.4%, and then when we get up here for the higher loading of silver nanowires, 3%. Color parameters, our materials, the Agent 10 has enough silver nanowires in it that it has more yellowish in color, but the other materials have pretty low amounts of color. And this is an advantage over other printable material like PDOT. The target applications for us, touch sensors are a big one. We're pretty much leaving this area for silver nanowire films and metal mesh films. And we're focusing on touch sensors, that area is really dominated by ITO and especially PDOT. So we're focusing our energy towards displacing those materials in touch interfaces that are not full-blown touch screens necessarily, but touch buttons, touch sliders, and resistive touchscreens. Heaters is a big opportunity. Transparent heaters, this opportunity is being driven by the automotive industry, which needs to have clear lenses and clear windows for optical and RF sensors to peer through. And if they are fogged up, if they are iced up, it's a safety issue. So there's a big market pull for a material solution like ours in the automotive industry. Antennas and RF shielding, 5G and the IoT are creating big opportunities here. In antennas, there's so many antennas that are being put in place and so many antennas infrastructure that's needs to be replaced because of 5G that the people really want to hide these antennas. They don't want them to be so noticeable. And so a transparent antenna is valued. And we have, with our technology, we help enable transparent, flexible, conformable antennas that are affordable and just as high in performance as the non-transparent printed circuit board antennas. IoT, there's all kinds of devices that will be IoT enabled, and they don't want the antenna to take all the attention from the device or the product. So a transparent antenna would be valued. RF shielding, we have RF shielding film products that we expect to be embedded inside cell phones that will protect users from unnecessary exposure to RF power, which is increasingly a concern, especially with 5G, but not detract from the antenna performance. And that's not a very easy thing to do, but we have a solution that does that. So for touch sensors, we see PDOT, not ITO, as the real enemy. And we are focusing on exploiting the pain points associated with PDOT, blue color, inconsistent print quality, poor environmental stability. There's another pain point as well, is that the sheet resistance and transparency properties of the PDOT are not nearly as good as ITO and not nearly as good as silver nanowire and metal mesh. So we have a two-pronged approach to attack PDOT. First is to introduce a carbon nanotube only ink product that can be printed onto conventional plastic films. This product will have similar sheet resistance and transparency like PDOT, but has neutral color, prints very consistently, and has outstanding environmental stability. So this product is coming to market in Q1 of 2020. And we ultimately expect to trade up customers that adopt this solution to the carbon nanotube hybrid solution, Agent 75, which also offers much lower sheet resistance and much higher visible light transmittance. Here's an example of a resistive touchscreen made from our Agent 75, and it's a nice application. There's a lot more capacitive touchscreens out in the world today, but there's plenty of resistive touchscreens. So we would love to move those touchscreens up to use the Agent materials. Transparent heaters are really hot. In fact, that's proven at our booth. We have booth 107. This has been the hottest item at our booth. We are displaying a transparent heater. We have demonstrated transparent heaters that can achieve power densities in excess of 3,000 watts per square meter. This can generate temperatures that are well above the boiling point of water. Now, we really just need to be able to melt ice on a windshield or a lens, but we could boil water on these transparent heaters. Thermoformability is another really important thing, and carbon nanotube materials are one of the most robust materials on Earth. Strongest, they're strong, they're flexible, they're tough. Adding these materials to metal mesh and adding these materials to silver nanowire films greatly enhance the thermoformability of those materials. We have done some work. We expect to do a lot more work with collaboration partners, but we have observed in thermoforming less than 20% change in the sheet resistance resulting from thermoforming. A lot of that percentage change is attributable to dimensional change, not material property change. And at this particular example met our customers' expectations. So the ability to thermoform, the ability to have affordable processing, the ability to tailor the structure of the transparent conductive film, those are big competitive advantages of the agent technology. Our printed electronics platform is, we make all of our own carbon nanotube materials. We have proprietary ink vehicle technology. Both our carbon nanotube synthesis and our ink chemistry are patented. The ink technology is called V2V, viscous fluid transitioning to vapor. We synthesize this ink vehicle and to make a high molecular weight, highly viscous material. But at 80 degrees C, it decomposes to its precursors, which at 80 degrees C are volatile. So this ink vehicle completely evaporates at 80 to 100 degrees C, which is low enough temperature for the plastic film substrates. Another thing is we have technology that allows us to disperse carbon nanotube organic paste into this ink vehicle without the use of surfactants. So when we print this ink onto a substrate, we're not leaving behind surfactants, which are viewed as a contaminant for the printed electronics. We use polymer binders, and this is an area of active research for us. Currently, we're using an acrylic polymer binder, which is really nice for thermoforming. We also, during 2020, expect to bring to market a UV curable polymer binder, which will have even better encapsulation properties and very good scratch resistance. We're also developing an elastomeric polymer binder for stretchable wearables applications. Of course, these inks are designed for screen printing, which is a very convenient way to make printed electronics. Our business model, first and foremost, we aim to make and sell printed electronics materials. We want to sell jugs of inks and rolls of film. We don't necessarily need to make the rolls of films ourselves. In fact, we prefer not to. We prefer to source the silver nanowire film and the metal mesh film from best-in-class suppliers. We'll make all the carbon nanotubes, we'll make all the inks, but we aim to have strategic supply partnerships here. And we are in the process of developing those partnerships. In addition, on the supply side, we are developing partnerships in the value chain. We call them preferred integration partners. These are companies that have the ability to design in our printed electronics materials into our target applications, touch sensors, antennas, heaters, and so on. They also have the ability to fabricate flexible printed circuits from our materials. Our goal during the year 2020 is to have 50 certified preferred integration partners around the world that are capable of converting our materials into agent flexible printed transparent circuits. To accelerate adoption, however, we do make prototypes. We have a facility in the Boston area that can make patterned transparent conductive films for the preferred integration partners and for customers. We can make flexible printed circuits with other layers printed onto them. We can make fully functional devices as needed. We can also do early stage production of flexible, patterned transparent conductive films. We're doing this to stimulate demand and to get design-in wins with the OEMs Tier 1 and Tier 2, but ultimately we expect the printed integration partners to do the mass production of the flexible printed circuits and assemblies. This is a picture of the printing press line that we have in our facility in the Boston area. It's in a Class 1000 clean room. We've standardized on 12-inch by 24-inch sheet size. It's a state-of-the-art Atma screen printing press with dual cameras that allow for excellent layer-to-layer alignment. It's fully automated so we can capture all the printing process recipes. We have a conveyorized oven that can do convection drying, infrared drying, and also UV curing. We also have an etcher. This is an industry standard chem-cut etcher. It's a conveyorized etcher. We use ferric nitrate etchant. Most common etchant for copper is cupric chloride or ferric chloride, but ferric nitrate is a very good etchant for silver, and it also is a decent etchant for copper. And so we use ferric nitrate etchant because it can etch both the silver nanowires and also the copper metal meshes. This is just a few images of equipment we have in our Norman, Oklahoma plant. This is the scale. These are about 40 feet high of our carbon nanotube synthesis reactors. And this is our operation for purifying the carbon nanotubes to remove the catalyst material after synthesis, recover the carbon nanotubes, and then further process them into inks. Thank you. Are there any questions? Yes?
Two questions. One is, you gave a cost estimate of your material, including patterning. Does this apply also to the best one you showed with the 1 per square, or would that be under the previous price?
That's a higher price than that one. Yeah, and that price is right now, I'd rather not give you a price on that one until we certify who's going to supply us the metal mesh, because that cost is dominated by the metal mesh material.
And the second question is, do you think your materials are going to be smooth enough that you can use them as electrodes and deposit thin layers on top?
Good question. Current versions of our materials are not smooth enough for like transparent electrode for OLED or OPV application, which require very thin electrode spacing. I think we may have a future generation that could do that, but right now our focus is on these applications. There's plenty of market for us to penetrate in the applications that we're targeting.